Quantizing your KV cache doesn't hurt. If you're coding, you're using Quen 27B, you can go down to Q4 with no degradation in performance. I'm going to load up the graph here, and so if you're really allergic to hearing the word Q4 KV cache, you can close out of the video now. But this is the performance. It's flat. We're going to go over some experiments I ran overnight, about 24 hours of GPU time, cranking through differences between Q4, Q8, and F16 on a bunch of different tasks. And we're going to go over how I think is the right way to approach a question like this, and the ways I have tried to find counterexamples to this. I believe that a falsifiable hypothesis is worth its weight in gold. Here's the hypothesis, all right? And this is the unbiased approach to questions like this. Q4 performs about as well as F16 on software engineering problems. It reaches similar conclusions, reaches the same code on like 95% of coding tasks, up to 100K context use. What would we expect if this wasn't true? Well, it's going to do a poor job on a bunch of tasks here. As you go up to Q8, it'll perform better. And then we'll have this sort of, if we plotted each task as a little dot here, and then we could have a nice line that goes up as the quantization gets bigger. And we don't see that. What we see looks more like just a flat line where the performance is the same all the way across. Now we're getting somewhere. If you came to me and said, look, Bob, I found this class of problems, okay? And if you ask the F16 version to implement Dropbox and do it in the Swift programming language and make sure that every line of code rhymes in an A-B rhyme scheme, and the F16 can do it and the Q4 can't, well then we can throw out the hypothesis, right? And we can say, well, we found a class of problems where it doesn't fit. And so when I think about what are the right parameters that I want to use in production, I 100% believe that we should be using this approach. And it generalizes very well outside of local LLMs. I get a lot of comments on YouTube where people are saying, and I'm going to engage in good faith with the YouTube comment section, something I don't recommend that you do. But if you come to me and you say, look, you're stupid, Q4 is stupid, I stopped watching the video 10 seconds in, thanks for not wasting my time. I think that's pretty funny to do that. And it's at odds with this, come up with a hypothesis and test it strategy that I do recommend. And so maybe this is the point where I should go over my credentials and my background and my 7-page CV. And since I don't have a resume, it's a CV, I'm good. And you should trust me, bro. Unbiased Bob knows this KV quant stuff cold. And that is exactly the opposite point of this channel. The point is that you should measure it on your own tasks and your own hardware. And partly because it's just fun. It's really exciting to have these really complicated and incredible machines, this amazing invention, this next token predictor. And to be able to run it at home, open source, is fantastic. And so that's my focus on this channel is let's measure it. Let's come up with a falsifiable hypothesis and test it and measure it. And so if one person watches this and says, you know what, I'm curious about this whole KV cache quant thing, like, is Q4 really bad? If one person says, I'm going to download Llama Server, I'm going to get 27B, and I'm going to use curl, and I'm going to hit it with some requests, and then maybe I'm going to have Claude Opus drive it, have Claude Opus drive it to write something real for me. And maybe I'll write my own bench set. Maybe someone's going to write their own, Bob bench or whatever. So anyways, if one person goes off and creates Bob bench, then this video will be a success. Anyways, sorry for my diatribe. 2 more graphs. One really interesting paper coming out of Meta, Facebook AI research. I don't know what they call it these days. And then we'll be done. I ran 2 experiments last night. One on Apple Silicon, where I have a lot more RAM available to me. I have a Mac Studio. I'm very happy to have 96 gigabytes on that guy. I wish I had the 128 version though. And so on that one, I ran a full 256K context run across F16, Q8, and Q4 on the hardest tasks in Bob bench. And so these are particle simulators. And we'll play some of that video on screen over my face right now. Given a black box of a particle simulator implementation, and then they have to deduce what the rules of physics are and write emitters that follow the rules of like gravity and charge and attraction, like a bunch of different effects in the little physics sandbox. And the black box task is quite difficult, and the other ones are just varying skill levels of the same type of task. And so if we're going to take this claim at face value that like Q4 is absolutely lobotomized and terrible, then I would expect to not only see failures on these tasks, I would expect to see things like malformed tool calls, like emojis getting printed, like the stuff you see with really high temperature, where it's just going completely off the rails, and it doesn't occur. And there's one interesting finding, like the performance is exactly the same across all these tasks. And this ran overnight on Apple Silicon. Let's see, I have some stats here. Okay, yeah, 200,000 output tokens. That's actually not a lot. Oh, I see. I think they spent most of their time on the black box tasks, and those were like 80K context. And then the other ones didn't require as much context to solve. And so, yeah, honestly, I mean, this is a flaw in my methodology, is that I didn't make the task consume the full 256 context. Now, I don't like my agents to go that far, whether it's Opus or whether it's a 27B quant or whatever. I want them to work within the first 25% of that context window, ideally less, and then boom, you cut it, and then you start a new freshly scoped agent to do the next task. But this is something that deserves, it deserves to be looked at deeper, is that my task didn't use the full window. So maybe the YouTube commenters are right. But anyways, look at this column here. So in this case, the Q4 version did better. All right, it got 5 points. It got 10 points, and the other guys got 5 points with a timeout. So, and if you look at the reasoning in the fix bugs, and it has like a bug in the particle simulator, and asks the agent to go address it. And so these guys, larger quant, were less decisive, and the Q4 model it didn't waffle as much. It wasn't saying, oh, well, maybe I should do this. No, actually, wait, that we see a lot with Quinn. That's why it actually scored better. And so if you look at the actual scores on this Mac test, it got a higher score. The Q4 is just better because it doesn't waffle as much. If it truly doesn't waffle as much, that's a behavioral difference that we just measured between Q4 and Q8. But for me, honestly, they all went off. They all inspected the behavior of the existing implementation. They all dealt with a bunch of like floating point issues and arithmetic and writing code and testing code. They all had the same behavior, whether it was the Q4, the Q8, or the F16. And so let's come up and look at the 4090 tests that I kicked off around the same time yesterday. This would have been on August 18th. And so each of these rows is a task. And so here, the psim black box. Let's zoom in on this guy for a second. So these 3 dots stacked are indicating that both models tried the task 3 times, and orange is the Q4, and blue is the F16. So they tried it 3 times and failed. So they just couldn't do the task. Same behavior, whether it was Q4 or F16. Now that's not as interesting as the other ones. And so if we look at this task from SweBench PyTest task, and there is an F16 issue where it's probably just noise, but one of the F16 arms failed, and otherwise they just kind of cranked through it. Same Py2C mini VM. This is a task where you're implementing a virtual machine in C. It's challenging, it's difficult, it's got a lot of edge cases, and they all aced it. Whether it was the Q4 or the F16 didn't matter. Format spec mini. This is a gnarly test where you're converting stuff into JSON. It's got a lot of edge cases and a lot of different ways. You're taking like an arbitrary Python dict and formatting it into JSON based on a bunch of specifications, and it's also another challenging task. And it looks the same to me. When I look at this, I don't see any indication that the Q4 is severely degraded, lobotomized, whatever you want to say. Here are the parameters that I used on this run. This particular one is, let's see, what's the context like? Yeah, so this is from my NVIDIA run. So it has a 64K context window because I just don't have enough VRAM on that box. And so some of these tasks that ran on the 4090 ran out of context and they just quit running, which was an acceptable failure mode, like the PSIM black box or black box sealed. But these ones are able to be completed within the 64K context that was available to the agent. And note that on the Mac, since I have more RAM, those guys got the full 256 context. So anyways, yeah, Q4. Ooh, it's so scary. That is why I use the Q4 context, and I'm totally willing to be, to have this debunked or disproved or whatever. But there's this paper that this reminded me of, and it's called Quantized Reasoning Models Think They Need to Think Longer, but They Do Not. And this is from Facebook AI Research or Meta. Does it say on this one? No, it doesn't say. But anyways, the point is that they looked at Qwen 3, I think, and they're really small models, 1.5B up to 32B. And it was an older generation of Qwen that they were testing, but I think it should generalize. And so here's their result. They say that you get better accuracy if you stop these things from thinking. And the way that you stop them from overthinking in this paper is super, super fun. They have these waffle tokens. I call them waffle tokens, but I don't think they do. And so perhaps, maybe, however, wait, but regardless, still, another doubt. And if they reach into the sampling mechanism of their inference engine, of Llama Server or whatever, and they just nerf the ability of the model to emit this, and they say, okay, you can't emit these tokens anymore. And it stops this degenerate failure mode where it never terminates reasoning, and they get better results. So as far as I know, this is not an option in Llama Server. I have it on a branch somewhere, and I tried a couple different versions of this. I want to revisit this because I think this could help with possibly even extreme quants of the 27B. I think, and I don't have evidence for this, but my understanding is that the larger the model gets, the more resilient to quantization it can be. And so maybe there's a chance I could run a 70 billion parameter model on a 24 gig graphics card if you can go down to Q2. I don't know if the math checks out for that, but maybe larger models can run and with some techniques like this, maybe you can get acceptable performance from it. So anyways, I recommend reading this paper. It's interesting. It was published this year in like May, and it uses these really old models, and I don't really understand that because they could have used Qwen 3.5 and they did not. But that's all I've got today. Use the Q4 quant. It's fine.